Welcome to Python tutorial 3 of the course Time Dependent Quantum Chemistry. In this tutorial, we will go over Fourier transform of a wave function. How to, if I have a wave function already defined on the x grid numerically, then how to get the Fourier transform of that wave function. We need to do this Fourier transform of a wave function in many occasions, particularly while solving while finding out the numerical solution to the TDSE. So, we will go over it. In quantum mechanics, the Fourier transform is used to relate the position space and the momentum space wave function. So, I have to, by doing this Fourier transform, what we do basically in quantum mechanics particularly very frequently, to relate the position space and the momentum space wave functions so position space so if we want to convert from position space, so in the position space we know that we are expressing the wave function as psi xt, and if we want to convert it to momentum space, so this is the equation which we use, this is the Fourier transform equation we use to for the forward Fourier transform. On the other hand, and we know that this kind of wave function in position space in the programming language they can be presented in the grid representation. So, we will see how to do that. So, this is your x grid. In the x grid you have a wave function defined, that is the psi xt, and if you want to convert it to momentum space, which means now in the momentum space it is going to be the same number of grid window. So, the same grid window, which means number of elements should be the same, but now this is your x grid and this is your k grid. K grid is representing the momentum space, and in the momentum space we have to find out what would be the representation of the wave function, and this is going to be phi kt. So, position to momentum space Fourier transform, and then inverse Fourier transform will give me again momentum space to position space. So, one can convert these two representations very easily by doing this Fourier transform. The position space represents the x space, which is the coordinate space, and momentum space represents the k space, where momentum space, this k is defined by 2 pi by lambda, which we will see why the definitions are like that, and we know that 1 by lambda is a wave number, and because it is wave number and it is multiplied by 2 pi, that is why this k is considered to be the angular wave number. So, angular wave number is representing the momentum space, which is nothing but 2 pi xi. Xi is the we will see that it is the frequency component which we are presenting here. So, the meaning of these equations or representation will be cleared in the next slide. Let us assume that I have a periodic spatial structure. We are familiar with plane wave in time, and plane wave is represented by cos omega naught t like this, and we know that this is the angular frequency which is showing per second how many angular cycles you have, and how quickly it is actually changing the variation in the t axis. Similarly, in the spatial structure, when you have a spatial structure, one can think about, okay, if it is a 2-dimensional spatial structure x y, then one can think of periodic variation. So, where the line is, these line positions are actually the higher position, it is more like on the x axis it is now going to be like this. So let's say there is an hill, and then there is a valley, then there is a hill, then there is a valley. That this is the way periodic structure is changing on the space. And if I have the change, then the change is controlled by how quickly the change is happening, that is controlled by this k value. So this periodic spatial structure can be represented by this simple k cos kx, and if we can represent by cos kx, then kx represents the phase of the, so this kx is going to be the phase of the spatial periodic structure. It is called phase, and phase is nothing but an angle. So this is representing an angle. And this is why k, this k is representing the magnitude of the wave vector characterizing the nature of the periodic structure. This periodic structure not in time domain, it is in the space domain. So this is a spatial periodic structure. What we can note here is that if we have a lambda displacement, linear displacement, this is linear displacement, this is equivalent to 2 pi phase shift. So this linear displacement along this direction can be correlated with an angular shift. So what we can see here, this point, this arrow is now making 2 pi angle. Once this is making 2 pi angle, I am actually moving from here to here. So this linear displacement can be conveniently represented with respect to what is the phase advancement I have in angle, in terms of angle. So if it is so, then I will be able to write down k, this linear advancement x plus lambda equals nothing but I had kx previous phase plus 2 pi phase, extra phase I am adding. Or in other words, I can simplify this equation as 2 pi by lambda. So what we are seeing is that k is, the magnitude of k is related to 2 pi by lambda, which is nothing but 1 by lambda. This is 2 pi. This xi function we use, xi notation, to represent this spatial frequency. So this xi is called the spatial frequency, which is representing how quickly the periodic spatial structure repeats per unit length. We remember that in the time domain we have used nu as the frequency, but here in the spatial domain we are using this xi as the spatial frequency. So, if we have that, then what we see is that this k is related to this spatial frequency xi, and how to get this spatial frequency we will go over it. So, and this k is representing the momentum space in quantum mechanics. So, what we will do here in order to convert this from position space to momentum space and momentum space to position space, which is the inverse Fourier transform, we will make use of an efficient algorithm. It is called fast Fourier transform algorithm. This is called, so, numerical implementation of Fourier transform through discrete Fourier transform. It is called fast Fourier transform, FST, fast Fourier transform. So, this is the algorithm which we use, FFT algorithm, to transfer this function. So, basic idea is that this is an analytical expression, and one cannot use this kind of analytical expression. We have to define, we cannot use this minus infinity to plus infinity limit. We have to always think about finite limit. So, in the finite domain, we will say that x has a minimum value and x has a maximum value, and this is the grid which we create first, and on this grid we will represent psi x t, and we know that how to represent this psi x t. Once we represent that psi x t in the position space. So, this is the step number 1, how we are going to perform this Fourier transform with the help of fast Fourier transform algorithm. So, first we have to represent the wave function in a finite grid, and we know how to select those finite grids. And when you are selecting the finite grids, we have to make sure that at the boundary of the grid the wave function should go to 0. And because we cannot use minus infinity to plus infinity limit in the finite grid in the numerical method. Now, once we have represented the wave function in the x grid, then all we need to do is that there are two things we have to find out. There are two points we have to take care. First point is going to be, we have to now create the k grid. And on this k grid we will be representing the wave function, Fourier transform wave function. So, we have to construct the k grid, that is the second step, and another step we have to consider is the Fourier transform that wave function and then present it. So, I have to Fourier transform. So, psi x t has to be converted to phi k t. This has to be converted, and this on this constructed k grid we have to now represent this phi k t. And when we are constructing this k grid, we cannot just randomly construct the k grid. There is a particular protocol or particular restrictions we have for the Fourier transform of the grid, and that we will go over very soon. But the bottom line is that we have to follow two different steps. First, we have to convert the x grid to k grid, and then we have to convert the function, which is the Fourier transform, to the to the k grid, and then we can plot this as a x and y. So, x is going to be, so not x and y, it is going to be now k versus your function is k t. This is what we can plot. So, this is the basic idea behind this entire procedure of fast Fourier transform algorithm. So, let us look at the construction of the Fourier grid or reciprocal grid or k grid. They are synonymous, and often we use reciprocal grid to represent the K grid or Fourier grid. So, what we while constructing this the K grid first, we will first note down an interesting correspondence between the x domain and K domain. So, this is your x domain which we have to create, and we know how to create x domain with the help of a range functionality of psi pi, and while we are constructing the K grid, we have to follow a particular procedure. So, what are the correspondences we have between this x grid and K grid? The first correspondence is that the same n number of grid points should be present in both x and K representations. So, in the x grid, when you have represented the x grid, let us say this is starting from x naught and this is going to x n minus 1, which means that I have n number, n total n grid points we have in the x grid. In that case, when we will be constructing the K grid, I should have the same grid window. It is called grid window, which means that the same number of grid elements we should have. So, this is going to be n number of grid points. So, that is the first correspondence we have understood when we are converting x grid to K grid. Second thing, that when you are selecting, so here I have n number, here I have n number, but when you are selecting this delta k, I cannot select delta k randomly. So, second correspondence is that this delta k, which is defining the spacing between two adjacent grid points in the K grid. In the K grid, this is the spacing between two grid points, adjacent grid points. Delta k cannot be randomly selected. In fact, theory of discrete Fourier transform abbreviated as DFT, discrete Fourier transform, establishes a relation which must be fulfilled while transforming this x grid to K grid. So, when I am transforming this delta k and delta x, they are related, and how they are related, the proof will not be given here, is not given here, just use the final result, and the proof comes from the discrete Fourier transform methodology. This discrete Fourier transform methodology is implemented in through this FFT algorithm. So, the algorithm which we are going to use, FFT algorithm, this FFT algorithm is based on the discrete Fourier transform theory, and it shows that delta k delta x has to be 2 pi by n. N is the number of grid points we have, or in other words, this delta k, when I am selecting delta k, that has to be 2 pi by n delta x. That is an restriction of the Fourier transform. So, we have to remember this two, this restriction while we are transforming the x grid to k grid. Finally, this is the final step. So, based on this restriction, we have been able to create this k grid, and once we have got the k grid, we have to specify it how to get this k grid. The fast Fourier transform algorithm, the FFT algorithm, this is the computer algorithm based on discrete Fourier transform theory. It will allow us to sample the spatial frequencies defined by this, and that spatial frequency will be defined by this expression, where f represents, this f represents a list, or we can call it an array of spatial frequency components, which is given by this. It is going to be 0, 1, 2, then n by 2 minus 1, then minus n by 2, then minus n by 2 plus 1, up to minus 1. If n is even, or if it is odd, then I have to use, it is going to be 0, 1, 2, then n minus 1 by 2, then n minus 1 by 2, minus n minus 1 by 2, then minus n minus 1 by 2 plus 1, up to minus 1 if n is odd. And so, this is the way FFT will create the frequency components, and once we know the frequency components, we know how to get the k grid points. So, k grid points will be just multiplied by this frequency component needs to be multiplied by 2 pi. So, then we can get the k grid points here. That is the way we are going to construct. So, what we see that FFT algorithm or DFT, this Fourier transform, this discrete Fourier transforms will actually create the frequency components, which is first is 0, then the then is going to be 1, 2 and so on. Okay. And we have also negative components as well, because negative components comes from the fact that in the Fourier transform it is a complex notation, and once complex notation is converted, we get the negative frequencies as well. In practical purpose, we can neglect those negative frequencies, but for the completeness of the theory, negative components should be there. We will continue this session in the next class.